Hello friends, I welcome you all on India's largest e-learning educational platform, that is Gradeup. Today in this third session for electrical machines revision for your GATE 2020 examination, we are going to take up the basic part of induction machine and we will be taking related questions also. Now let us go forward. Now there is a brief introduction of myself. My name is Ashutosh Saxena. I have more than 9 years of teaching experience. I completed my M.Tech in 2010 from IIT BHU. My areas of expertise are electrical machines, power system, electromagnetic field theory, material science and engineering ethics. I have written a couple of books also that you can see on your screen. Now let us move forward. Now see, the number on your screen is very important. Only 14 days are left for your GATE examination. So you should be really on your toes and you should always try to utilize every bit of your time for your examination. Now as you can see on the screen, we have offered a very value product for your preparation on this 26th January on the Republic Day. As you can see on the screen, up to 50% off on your fee, and it is going to be really rewarding. Just go to our app or the website and get maximum benefit out of this offer. Now for the Vision 2021, a course for engineering services and GATE aspirants, this is really going to be a big opportunity, and as you can see on your screen, the offer which is given to you, the discount is very significant, so you can avail this offer going to our website or the app. Now as you can see, let me remind you again that we are conducting the mega mock challenge again for your GATE 2020 examination. As you can see, for EC and mechanical students, the window will be open from 29th January to 30th January for 24 hours. And if you see for electrical, civil and CS students, it will be open from 5th of February to 6th of February. So you can log into our app or the website and you can register yourself and you can avail this big opportunity, that is Mega Mock Challenge. Good morning all the candidates who are live now. Good evening Priya, good evening Mr. Kayur. All the candidates who are live now. Now let us start the next part that we have to discuss, but before I start taking the questions for induction machine, let me tell you and give you a brief idea about induction machine. That is very important. I'll be going really fast, and if you have any doubt meanwhile, you can put your doubt in the comment section and I will try to cover basic part of induction machine in this session. Now let us first start. Induction machine. Basically, we are focusing on three-phase induction motor. Now, the first question is, why we are focusing on induction motor, not induction generator? Now, please try to understand that induction machine operates on the principle of induction. That is why we are saying induction machine is a singly excited machine. So that if you compare your induction machine with the synchronous machine or the commutator machine, that is DC machine, both the synchronous and the DC machines are doubly excited. But if you see the induction machine works on the principle of induction. We will see why we are saying so in due course of time, but you should understand that induction machine is called a singly excited machine. because only one of the winding among stator and rotor is being energized, and in the other winding the currents are going to be induced, which are going to create a flux, and that flux is going to interact with the flux in the winding on which the supply is given. And let me tell you the basic operating principle of any machine. You should have two flux which are going to interact. If there are two fluxes which are going to interact, your machine is going to operate. Now there is one candidate, he is asking, sir, what is the major difference between induction motor and synchronous machine? Let me tell you the basic part of induction machine, and definitely you will be able to understand this difference between synchronous and induction. Please have a bit of patience. Hello Mr. Arjun, good evening. Hello Mr. Shabas, how are you? Now let us go further and please understand that if you see your induction generator only generates real power. That is, it requires reactive power from an external source. This is the reason, and there is one more reason, that induction machine operates at asynchronous speed. That is why it is also called asynchronous machine. Now if you go with these 2 points, okay, there is one candidate, Mr. Mahesh, he is asking, sir, armature winding placed on rotor or stator. Now all the candidates who are live, please try to have a bit of patience. In 5 or 10 minutes, we are going to discuss the basic part of induction machine. Each and everything we will discuss that is related to your exam, and all your doubts are going to be solved. You just need to give a little bit of attention and focus. Hello Mr. Arvind, how are you? Now there is one candidate, Mr. Bikram, he is asking, sir, for same rating of cylindrical and salient pole machine, which one is more efficient? See, right now we are focusing on induction machine, and you should also focus on induction machine. Synchronous we will cover in the next session. Then we will discuss the difference between cylindrical and salient pole machine. Okay. Right now, you please focus on what I am trying to discuss. Because of these two reasons, if you see, because of these two reasons, the induction generator can only generate real power, and it requires reactive power from external source. And the other point is, induction machine operates at asynchronous speed. This is the reason induction generator is suitable for non-conventional energy resources, and that is why most of the generators in the power system are synchronous generator. Now this is the reason why we are focusing on motor when we are dealing with the induction machine, because if you see, the most wide application of induction machine is going to be induction motor, not the induction generator, because if you see the nature of induction generator, the induction generator requires reactive power from an external source. It cannot generate reactive power. The reason is that induction generator is also going to work on the principle of induction. And if it is working on the principle of induction, it requires heavy reactive power requirement that needs to be supplied from an external source. So now let us start three-phase induction motor. Now let me first give you an idea how your induction motor is going to operate, because most of the candidates are having a doubt how your induction motor is going to function. Now let us try to understand. Suppose this is your stator and this is your rotor. Now I am saying the stator is given three-phase supply input. Now step by step we'll try to understand. Okay. Mr. Mahesh, please have patience. Let me discuss the basic part, then you will be able to answer all your doubts. Now the first thing is, for induction motor we are having a stator that is connected to the yoke. It is stationary, and we are having a rotating body or rotating part which we are calling as rotor. Now please try to understand that the stator windings are given a three-phase supply input, and we are saying that the stator windings are distributed in space 120 degree apart. Now you should know this principle that whenever a three-phase supply, a balanced three-phase supply, the idea is whenever a three-phase balanced supply is given to a three-phase distributed winding 120 degree apart in space, then it is going to produce a rotating magnetic field. This we are calling as stator RMF. That is the rotating magnetic field of the stator. So the idea is that if you are providing a three-phase supply input to your stator winding, and the stator windings are distributed in space 120 degree apart, a stator rotating magnetic field is going to be established. And if you see the derivation part that is available in your standard books or your notes, wherever you are reading this stator rotating magnetic fields has a magnitude that is 1.5 times phi m, which is constant, and it is going to rotate at synchronous speed. Now you please try to understand, when this rotating magnetic field of the stator is present in between the stator and rotor air gap, this we are calling as air gap, the rotor windings are going to cut this flux, yes or no? And because this rotating magnetic field is rotating in nature, so they are going to induce currents in the rotor windings. It means currents are induced in the rotor windings. Is it okay? Now, why we are saying currents are going to induce? The idea is because of the stator rotating magnetic field cutting the rotor windings or conductors, EMF is induced in rotor windings, and you please focus here that rotor windings are always short circuited in case of induction motor. So, if the EMF is going to induce in the rotor windings and rotor windings are short circuited, definitely currents that are induced currents flow in the rotor windings. Now, you please try to understand these rotor winding currents will again give rise to a rotor rotating magnetic field. Now, because of the interaction of stator and rotor rotating magnetic field, the motor starts rotating. Now, this is the basic idea how your induction motor is going to start. Good evening, Ms. Soumya. Now, there is one candidate, Mr. Bharat, he is saying, please explain it again. See, if you are interested, you can see this video again when I am offline because I am having very limited time. I think this is very simple. I will just give you a crisp revision of what I have covered. I am saying that if you are going to provide a three-phase input supply to the stator and the stator windings are distributed in space 120 degree apart, they are going to give rise to a stator rotating magnetic field which is having a magnitude of 1.55 m, which is constant, and it is rotating at a synchronous speed. Now, because this flux is rotating in nature, the windings are present in the rotor structure. So, the currents are going to induce in the rotor winding, because if you see, because of the stator rotating magnetic field cutting the rotor windings or conductors, EMF is going to induce in the rotor windings. And we know that for induction machine or induction motor, you can say the rotor windings are always short circuited. So, if the EMF is induced, windings are short circuited, circuit is complete, it is going to have induced currents. Now, these induced currents are going to have a rotor rotating magnetic field, which we are calling as rotor RMF. Now, for any machine to operate, the basic idea is you should have two interacting fluxes. Now, here the two interacting fluxes are stator and rotor rotating magnetic field, and the machine is going to operate. That is the basic idea. Now, let me give you some more few details about induction machine. Now, please understand, induction motor rotor always runs at a speed just below the synchronous speed. Now please try to understand, if nr is the speed of rotor and ns is the synchronous speed, we are saying that nr is very close to ns. But the most important point is nr never reaches the ns. What is the reason? Because if the rotor speed is going to be equal to synchronous speed, the rotor speed becoming equal to synchronous speed, there would be no relative motion between flux, that is stator rotating magnetic field, and rotor windings, so that no EMF or currents are induced in the rotor windings. This is why we always say that the rotor is going to rotate at a speed which is just below the synchronous speed. Now please try to understand that the rotor rotating magnetic field, that is RMF, rotates at, now please try to understand, we know that the stator magnetic field or the stator rotating magnetic field is rotating at the synchronous speed, but we want to know what is the speed at which the rotor rotating magnetic field is rotating. Now please try to understand, when you are finding the stator rotating magnetic field speed with respect to stator, how you are solving it? Ns is going to be 120 F by P. Yes or no? Now if you want to find the rotor rotating magnetic field speed with respect to the rotor or rotor windings, then it is going to be then it is going to be 120 Fr upon P. Now what is this Fr? This Fr is the frequency of induced currents in the rotor, which we are calling as slip frequency. Now, in order to understand the rotor rotating magnetic field speed, you should first understand what is slip and what is slip frequency. Now, please try to understand. For an induction machine, slip speed is defined as ns minus nr and percentage slip is defined as ns minus nr upon ns. I hope it is clear. Now please try to understand that if you want to write the frequency of supply at the stator circuit, then you are writing it as Pns upon 120, where P is the number of poles. Now if you want to find frequency of rotor induced currents, which we are saying as slip frequency, which we are calling as slip frequency, then it is going to be Fr is equal to P ns minus nr upon 120. What is the reason? Because if you are finding the supply frequency, you are using the synchronous speed. But if you see for the frequency of induced current, that is the slip frequency at the rotor circuit, you have to use the relative speed, that is the ns minus nr. Now if you find this relation, that is Fr upon F, it is going to be ns minus nr upon ns, which is simply going to be S. So slip frequency is going to be slip times the supply frequency. That is very, very important. Perfect, Mr. Mahesh. Now please try to understand, if you are having this information, it means if you want to write the rotating magnetic field, if you want to write the speed of the rotor RMF, it is going to be 120 Fr upon P, because at the rotor side or the rotor circuit, the frequency of the induced current is going to be Fr. So if you solve this, it is going to be 120 S times F upon P, or it is simply going to be SNS. This is very, very important. I hope it is clear to you. All the candidates who are live now, please tell me yes or no in the comment section. I am saying the speed of the rotor rotating magnetic field with respect to rotor, if you find, it is going to be S times Ns. Now let us try to find the speed of rotor rotating magnetic field with respect to the stator. Now you please try to understand that your rotor of the induction machine is not stationary. It itself is rotating at an r speed. So if you see the speed of the rotor rotating magnetic field with respect to stator, it is going to be n rotor RMF plus nr. If you want to find the actual speed with respect to the stator, that is the fixed frame of reference. Now if you see, it is going to be SNS plus nr, but you know that nr is equal to ns1 minus s. So you can write this as SNS plus ns 1 minus s. So it is coming out as ns. This is very, very important conclusion. It means that the rotor rotating magnetic field is also rotating at the synchronous speed with respect to the stator frame of reference. Now if you have understood this, let me draw a diagram. This we are calling as the stator frame of reference, which is fixed and if you see the rotor speed, it is going to be Nr, and if you see rotor rotating magnetic field speed, it is Ns, and if you see the stator rotating magnetic field speed, it is also Ns. But if you want suppose three-phase supply, three-phase input supply is given to the stator, and suppose this is your rotor. Now if you ask me the rotor rotating magnetic field speed with respect to rotor, then it is going to be slip times Ns. This understanding is very, very important. I hope it is clear, and if you have any doubt, you can ask me. Now there is one candidate, Mr. Parth, he is asking about the alternators. See, right now we are not discussing alternator. Alternator we will discuss in the next session. Okay. So you can take your doubt in the next session when we are discussing the alternators. Okay, Mr. Bharat, please let me know what is your doubt. We have to go forward because time is very less. I hope it is clear. Now let us try to understand that if you want to compare your induction machine, you tell me from which machine you can compare your induction machine. Because if you see, your induction machine is going to function simply like a transformer only, because if you see, your transformer is going to operate at the induction principle. Similarly, your induction machine is also going to operate at the induction principle. So if you ask me in one line to define what is an induction motor, I will say that induction motor is a rotating transformer whose secondary winding is always short circuited. I hope it is clear. Perfect, Miss Preeti. Yes, Mr. Venkatesh, the rotor rotating magnetic field is in synchronization to the stator rotating magnetic field. I hope it must be clear to you with whatever discussion we have right now. Perfect, Mr. Reddy. Perfect. So if you see, but there are some differences. What are that differences? The difference is induction motor has rotor windings always short circuited, and induction motor has exciting current. Like your transformer also, your induction motor is going to have exciting current, and that exciting current is 25 to 40% of the rated stator current, whereas if you see for a transformer, the exciting current, that is the no load current, I naught is just 2 to 5% of rated primary current. The reason is that your transformer is a static device and it has only induction. But if you see your induction motor, it is going to be induction plus rotation. In transformer, you only need to have induced currents in the secondary winding. But if you see for an induction machine, the induction principle is there and your rotor has to rotate to supply a real load connected to the shaft. It means it is going to draw more amount of exciting current from the supply. Now please try to understand that the induction motor has air gap as small as possible. This is the reason, because you want to reduce the amount of exciting current that is required for the operation of your induction motor. So for induction motor, we keep the air gap as low, as less as possible. That is the reason. Now if you have understood this, let us try to have the equivalent circuit diagram for your induction machine. The equivalent circuit diagram of the induction machine. So it is going to be very similar to your transformer equivalent circuit. So if you see, it is going to be something like this. It is going to be something like this. Now this is your E1, this is RC, this is XM, this is IW, this is I mu, this is I naught, this is I1, you can say this is R1 and this is X1, and this is your V supply. Now if you see the rotor circuit is going to be something like this. This is your E2, this is your R2, and this is X2. Now please try to understand how you are going to find E2, R2 and X2 for the rotor circuit. Please try to have this understanding. This is very, very important. Now if you see, if in this circuit we are saying F is the supply frequency, in this circuit if you see FR, that is the slip frequency, is going to be present. Now if you see the induced EMF, the induced EMF is going to be 4.44 F phi N, or you just write it T as the number of turns. It means if this frequency is going to be FR and FR is S times F, it simply means that this E2 is going to be slip times E20. What is E20? E20 is the EMF induced in the rotor windings when it is at stand still. Because if you see at the stand still condition, NR is going to be 0 and slip is going to be NS minus NR upon NS, that is going to be 1. So if the slip is going to be 1, the induced EMF is going to be only E20, and at any slip S, the induced EMF is going to be S time E20. Now if you see the rotor resistance R2, this is not going to depend upon the slip because R2 is a fixed quantity, so R2 is going to be same. But if you see the X value, the X value is given as, X is given as omega L, which is nothing but 2 pi FL. It means your X is going to be directly proportional to F. So if this is FR is equal to SF, it means X2 is going to be slip times X20. So I am writing it, X2 is equal to slip times X20. And this is nothing but the short circuit of rotor windings. Because the rotor windings are always short circuited, you will see only R2 and X2. Perfect. Now if you are okay with this, now we want to have the complete equivalent circuit. Now let me tell you, if you want the complete equivalent circuit, you have to connect this terminal to here. Yes or no? For that purpose, we are going to have some modifications. Now if you see the final equivalent circuit for induction machine or induction motor is going to be something like this. If you want to add these two circuits, you can add the stator. This is the stator circuit and this is the rotor circuit. Now if you want to add these two circuits, you should have the same frequency. Now for the same frequency, what I am trying to do, for this E20 and X20, I am removing the slip term. Let us see why. Because if you see, if the current is going to be I2, so how you are going to write the current I2? This I2 is going to be slip times E20 upon R2 plus J SX20. This you can write as I2 as, E20 upon R2 upon S plus JX20. It means if you take this slip term with the resistance, the E20 and X20 are going to be free from the frequency term or the slip term. So it means if you can modify your circuit like this, that this is going to be E1, this is going to be E20 dash. Why we are putting dash? Because like your transformer, you are referring your rotor circuit to the stator side, as you were referring in case of transformer, the secondary or primary side to the other side. So if you want to have the complete equivalent circuit, you have to refer the rotor side quantities to the stator side. And it is going to be R2 dash upon S, and this is going to be X20 dash, and this current is going to be I2 dash. This is RC, this is XM, this is R1, this is X1, this is I0, and this is going to be I1. This is going to be V1, that is the supply. Now one more important point, let me tell you that this circuit is the per phase representation of three-phase induction motor. So whenever you are going to solve the numericals, you should always take this thing in your mind, then it is always going to be per phase analysis. I hope it is clear. Now please try to understand some more concept about your induction machine. If this is your stator, and this is your rotor. Now suppose we are giving a 3-phase supply input to the stator. I hope it is clear. Now you please try to understand that the stator winding is going to have the stator copper losses and the core losses. What is the reason? If you see this equivalent circuit, the stator side is going to have the stator copper losses, and because of this it is going to have stator core losses. Now one of you student may get confused that why we are not taking into account the core losses in the rotor winding. Now let me tell you, in the rotor winding the frequency is going to be slip frequency, and because the slip value is very small, so the slip frequency in the rotor circuit is going to be very small. And you know that your core losses are going to be dependent upon the frequency, and if the frequency is very less, rotor side frequency is very less, so the core losses are going to be negligible. So all the core losses which are present in the machine, we are modeling at the stator side only. Now please try to understand, if you are giving the input supply, there is going to be some copper losses and core losses in the stator winding, and after that from this stator circuit to the rotor circuit, air gap power is being transferred. Air gap power is that power which is being transferred from the stator circuit to the rotor circuit. Now this air gap power is going to distribute in the copper losses in rotor and the mechanical power developed. I hope it is clear. This we are calling as PRC, that is the rotor copper losses, and this we are calling as PMD, that is the mechanical power developed in the rotor. Now this mechanical power developed is going to have friction and windage losses, and finally you are getting shaft mechanical output. This we are calling as PO. I hope it is clear. And this we are calling as friction and windage losses. I hope it is clear for all of you, all the candidates who are live now. Please tell me yes or no in the comment section whether you are getting this or not. Is it okay for you? I hope it is clear, all the candidates who are live now. Now you please understand that PG is given as tau D into omega S. Now what is tau D? Tau D is the developed torque. I am not saying it is the load torque, it is the developed torque, and this is the synchronous speed. This you can write as tau D into 2 pi ns upon 60. And if you want to write the mechanical power developed, it is going to be tau D into omega R. It is going to be tau D 2 pi nr upon 60. Now if you want to write the PG value, it is going to be rotor copper losses plus the mechanical power developed, and the rotor copper losses are going to be PG minus PMD. Now if you see, PG is going to be tau d 2 pi ns upon 60 minus tau d 2 pi nr upon 60. Now, if you find this ratio PRC upon PG, it is going to be simply NS minus NR upon NS, and it is simply going to be S times. So, if you find the relation, rotor copper losses are going to be slip times PG. This is very, very important understanding. I hope it is clear. Thank you, Mr. Shubham. Now, you please understand that the mechanical power developed can be again written as PG minus PRC, that is the rotor copper losses. This is slip times PG, so you can write it 1 minus S into PG, and this is going to be PMD. Now if you want to write PMD upon PRC, PMD is 1 minus SPG, and PRC is slip times PG, so it is going to be 1 minus S upon S, so it is going to be 1 minus S minus 1. Now why we are doing so? Now there is one candidate, Mr. Prasad, he is asking, sir, is rotor speed and rotor RMF is same? No, Mr. Prasad, if you are not comfortable with this understanding, please, when this video is offline, just go to the starting part where I have started the induction motor introduction, basic understanding. You will get your doubt clear. Rotor is rotating with the NR speed, NR. And if you see the rotor rotating magnetic field, it is also rotating at the synchronous speed as the stator rotating magnetic field. Lot of questions are being asked in the GATE examination and the engineering services examination on the same concept. I hope it is clear for you. Now you please understand why we are doing so. We are saying that the mechanical power developed is going to be this times the rotor copper losses. It means you can modify your circuit and separate. You can separate the mechanical power developed so you can draw the equivalent circuit diagram like this. And this is going to be, or better to remove this, directly put it here, otherwise you will get confused. Now this is going to be R1 X1, RC XM, this is going to be R2, this is going to be X2 0, and this is going to be R2 1 upon S minus 1, because if you add R2 and R2 1 upon S minus 1, R2 will get cancelled and you will simply get R2 by S. That is in the previous equivalent circuit. Now this is going to be R2 dash, X2 0 dash, R2 dash, and this is going to be E2 0 dash, and this is going to be E1. This is going to be IW, this is going to be I mu, this is going to be I naught, this is going to be I1, and this is going to be V1. So this is the final equivalent circuit for your induction motor. I hope it is clear. Now there is one candidate, Mr. Reddy, he is asking, sir, windage, friction and windage losses are not present, then the mechanical power is equal to shaft power. Perfectly. That you can call as rotational losses. if you subtract the rotational losses, let me tell you again, PMD is going to give you P naught plus P rotational losses. Now what is this P naught? This P naught is the tau load into 2 pi NR upon 60. You have to use this formula. Now what is tau load? Tau load is going to be, what is P naught? PMD minus P rotational. It is going to be PMD minus P rotational, and it is being divided by 2 pi ns upon 60. I hope it is clear to all of you. Now you can use this and find whatever required in your problem. I hope it is clear. Now we are running short of time. Let us quickly take some questions we'll take up, but before that let me discuss with you the torque equation that is very, very important. Now please try to understand. If you see the rotor copper losses, they are going to be 3 times V2, not V2, it is going to be E2S I2S cos phi 2S. Now if you see, it is going to be 3 times, and it is going to be slip times E2 0, and this is going to be slip times E2 0 upon under root R2 square plus X2 0 square, and this is cos phi is going to be R by Z, so it is going to be R2, and Z is going to be R2 square plus Sx2 0 square, and this is going to be again under root because it is R2 by Z. The rotor power factor is going to be R2 by Z. So Z is going to be this square under root. Now if you simplify this, it is going to be 3 times, it is going to be S square E2 0 square, it is going to be R2 upon R2 square Sx2 0 square. I hope it is clear. Now if you are having the rotor copper losses, very easily you can write PG, because PG is going to be 1 upon S times PRC. It is going to be 1 upon S 3 times E2 0 square. It is going to be slip square R2 upon R2 square plus Sx2 0 square. You can compare it with the previous equation. You have to simply put 1 by S. So S and S is going to be cancelled. S and S is going to be cancelled, and you will simply get 3E2 naught square, and it is going to be S times R2 upon R2 square Sx2 0 square. I hope it is clear. Now you know that developed torque is going to be Pg upon 2 pi ns upon 60. So if you want to write the torque formula, the developed torque is going to be 3E20 square upon 2 pi ns upon 60, and you will multiply it by SR2 upon R2 square Sx20 square. This is your general formula for the torque. Okay, Miss Rihanna, I will take up that question that you are saying, that for which you have found the answer, that I will take up in the next class. Let me conclude with very important information here regarding this torque equation. Then we will discuss the problem that you have solved in the next class. Now you please try to understand the general torque equation we are writing as 3E20 square upon 2 pi ns upon 60, and this is going to be slip times R2 upon R2 square Sx20 square. Now if you want to find the condition for maximum torque, and if you rearrange this equation, the condition for maximum torque is going to be R2 is equal to S x to 0, and if you see your tau max equation is going to be given as 3 e to 0 square upon 2 pi ns upon 60, and it is going to be 1 upon 2x to 0. So if you see this equation, you will say that maximum torque does not depend upon R2 or the rotor resistance. But you please keep this thing in your mind that Sm, that is the slip at maximum torque value, this is given as R2 upon x to 0. It means if you are increasing the rotor resistance, the slip at which you are getting the maximum torque is going to be increased. And you know that at the time of starting, slip is 1 because Nr is equal to 0. So if you apply the maximum torque condition, now the maximum torque condition at the starting, now you see that R2 is 1 to 2% of x to 0. So if you want maximum torque at starting, extra rotor resistance is required at the starting. So with this understanding, I am concluding this session here. Perfect, Miss Rihana. You are correct here, whatever I am writing here, the same thing you are saying. So I am concluding this session here. I wish you all the best, and let us get connected again in the next lecture for machine revision. In the next lecture, I will be giving you some input regarding the induction machine. The single phase induction motor also will discuss little points, and then we will take up some problems, and then we will go to synchronous and the transformer. I hope it is clear to you, and if you have any doubt, then you can ask your doubt in the comment section, or you can go to the Gradeup app and you can join us on the Gradeup platform. Thank you so much for your time. I hope this session was enriching for you. Please share this video, like this video as much as you can to all your friends and colleagues, just as to make this event a successful event. Thank you so much for your time.